Oh,
I
sorry.
usually start
Someone
2
from
minutes after. People will trickle down. As all of you know, people leave their offices exactly at the top of the hour to get down here, so they assume instantaneous travel time. So we'll let them arrive. Thank you all for being on time. You itching to get going?
As you wish.
All right. Let's get my cheat sheet. All right, I think we'll get started. Okay, looks like we're good. So thank you all for being here for the first colloquium of the semester, I believe. And so, you know, we're still doing the hybrid thing because that's the world we live in. Our first colloquium is given by our own professor, Louis Strigari, who has, when did you arrive? That's the part I forgot.
I know the year 2014. Yeah, so count.
2014. So Louis arrived in 2014. He's been working here since. I think one of the statements I heard that sums up his contributions to research best is that he's one of the few people who has contributed equally both in areas of astronomy and also high energy physics. He really exists sort of at the intersection between the two, studying both the interactions of fundamental particles like neutrinos and dark matter. I think we'll hear about those today, as well as observational tests that we might use to understand those. He has a long, storied, impressive career, so I have to have a cheat sheet. But he both held a NASA Hubble Prize Fellowship and then followed by something called one of the Kavli Center Fellowships and the Kavli Frontiers of Science Fellow. While he was here, he held an endowed chair, the Mitchell-Munnerlyn-Heap Chair, and you're awarded the APS Moore Foundation Convening Award now. He's had a steady stream of funding from every funding agency at the national level you can imagine, Department of Energy, NSF, NASA. Everybody wants a piece of Louis. And so
I want a piece of that too.
Right. And so I think today he's going to sum this up in 50 minutes or less, giving us a talk entitled The Dynamic Local Universe. So good luck with that.
I'll try. Yeah.
If you're on the Zoom, I will log into Zoom and try to watch for questions. So please raise your hand for that and we'll call you when there's a good chance to do it. I'll also try to repeat questions for the audience and run this thing around so you guys can ask questions and people online can hear it as well. So without further ado, take it away, Louis.
Okay, so thanks for the introduction and thanks everybody for being here in person and on Zoom. For those of you on Zoom, I'll try to project, but probably more importantly, I'll try to stand in front of the computer, which is really hard for me. It's really, really hard, but I will try my best. My inclination is to wander around the room. Yeah, so this is a topic, a theme of a seminar I've kind of been ideas I've been thinking about the past, well, really for a long time. I'm going to kind of focus this a little bit around the theme of measuring sort of the precise positions and velocities of stars in our own Milky Way galaxy, and sort of what these measurements are telling us about sort of new properties of the universe. So lots of these observations that I'll talk about have come from this fantastic satellite, which was launched a few years ago called the Gaia satellite, and that's shown here. What I'm going to do here is focus on the contributions of these observations to sort of the science of our local group of galaxies, the Milky Way, and our galaxies surrounding the Milky Way. Now, there's been volumes of literature on this field in the past few years. It's 50 minutes, Casey told me, so I certainly don't have time to go through all of that. What I will really do is focus a lot on the work that people in this audience have been doing and people here in our group, in particular students and postdocs. So it's going to be a very Texas A&M centric talk as much as possible. But, you know, I want to kind of give a broad introduction because we have a very wide range of people in this audience in terms of their backgrounds, presumably. So let's kind of start from the very beginning here. What you're looking at is a projected all sky picture of the sky picture taken by the Gaia satellite. Okay, so this image is based upon the positions of about 1 billion stars, the precise measurements of positions about 1 billion stars in the Milky Way galaxy. And in that prominent band you see in the center is our own Milky Way galaxy. Okay, so many, you know, stars live along this plane, amongst them our sun. So we live in this plane of the Milky Way galaxy. This image here was taken at optical wavelengths. Okay, So one could make a similar image at different wavelengths, right, that our eyeballs are not sensitive to, which sort of gives you different properties of the Milky Way galaxy. So you can kind of see here this image, right? There's denser spots, which represent sort of dense clumps of stars in some areas. You can kind of see colors of stars in some cases. But what I want to kind of get across here is what these types of observations are telling us about fundamental properties of the universe, and in particular, say, a particular fundamental property is on the nature of dark matter, because you can't see it, but all evidence points to a large dark matter halo that surrounds our Milky Way galaxy. So what I'm going to try to do here is understand how these measurements sort of give us information about that dark matter, amongst other things. Okay, so let's actually start from the very, very beginning, right? We have students in the audience. So you might have seen this, or will see this at some point in your Astronomy 101 class. So I talk about measuring the positions and velocities of stars. Well, how do astronomers actually do that? Okay, so one way you can do that for very nearby stars, that gets really bright. Yeah, okay, stand here. So one way you can actually do that for very nearby stars is measuring this effect called parallax. Okay, so what you do here is you measure, say, the position of a star relative to more distant background stars, say at some points in time. Do that again at some time later. Watch that foreground star kind of displace relative to the background star. Do a little bit of geometry, and then you can measure something called a parallax angle for that star, which tells you basically how that star displaces. And ultimately then, say if you know the distance between the Earth and the Sun, for example, which we do, you can use that to measure the distance to nearby stars. Okay, so that's a parallax. A typical parallax angle is about 0.1 arc seconds, which corresponds to a distance of about tens of light years. Okay, historical footnote, the first measurement, which you can't see behind the zoom bar, I don't think, but it was done by Bessel in 1838, the star 61 Cygni. It has a parallax of about 300 milliarc seconds, corresponding to distance of tens of light years or so. It turns out to be a dwarf star. Many stars have had their parallax measured via this method. They tend to all be like local stars, sort of in our solar neighborhood, right? You can only do this with nearby stars. Okay, so that's one component of so-called astrometry. The second component is, so that measures the positions and the distances of stars. The second one is the motions of stars. Okay, so how do astronomers measure motions of stars? Well, one method to do that is just look at spectral features in the star to see the Doppler shifts. So if it's moving forwards or backwards relative to you, you can actually measure its motion along your line of sight. Okay, so that's a straightforward way to measure how a star is moving. Of course, stars move in three-dimensional space, right? So the way that one can measure the transverse components of the motions of the star, or the so-called proper motions, is basically make a precise measurement of the position of a star at some epoch, come again, make another precise measurement sometime later, right? Position, right? Divided by time, change position divided by change of time is the velocity. So that's either called the proper motion or transverse velocity of the star, depending upon sort of what coordinates you're looking at. So so this proper motion or transverse velocity component, this is sort of the astrometric component that will be measured, that I'll really focus on here today. So the nearest stars have proper motions corresponding to about 0.1 arc seconds per year. Okay. If the trivia question is which star has the largest proper motion in the sky, the answer to that question is Barnard's star. It's very close. It's about two parsecs away from us, right? It has a proper motion of about 10 arc seconds per year. It's a dwarf star, measured a long time ago. Okay, so when I speak of parallaxes or proper motions, that's sort of falls under the umbrella of astrometry. Okay, so measuring positions and velocities of stars very precisely. Okay, so right. In some sense, you can do a lot of this astrometry from the ground, and as I mentioned, this goes back, a century or so, making these types of measurements. It turns out the best way to do astrometry is from space. Okay, there's many reasons for this. One obvious reason is you just get rid of the atmosphere, but of course, this is an incredible technical feat to try to do this. The first space-based astrometric mission was the Hipparcos satellite, which was launched in 1989. It was launched into a highly elliptical orbit, and it had a 4-year data-taking mission, and it made many fundamental contributions to astronomy and astrophysics. amongst them sort of understanding the position of our sun in the Milky Way galaxy. Okay, so for example, combining these astrometric measurements from Hipparcos with other measurements that we've made through telescopes, one can determine that the sun is about 8 kiloparsecs away from the galactic center, as indicated here. It's about 20 parsecs above the midplane of the galaxy. The sun is moving with a speed of about 220 kilometers per second around the Milky Way galaxy. Okay, and sort of that 220 kilometers per second is sort of the group of stars sort of around the sun on average, like how fast they're moving. The sun moves actually at about 20 kilometers per second with a so-called peculiar motion relative to that circular velocity, and that's indicated here. And those measurements really came into focus because we were able to measure sort of precise positions and velocities of local stars and sort of the kinematic motion of our sun relative to that. Okay, so right, so that's how astrometry from space started happening. Let's fast forward again now to where we are in the present time. So the predecessor to Hipparcos is the Gaia satellite, which is many times more sensitive than Hipparcos. So Gaia was launched in 2013, right? It currently sits at the L2 Lagrange points. And if you're like me and you can never remember which Lagrange point is which, that's on, let's see, the other side of the Earth relative to the sun. So it just sits there. Okay, so Gaia will improve upon Hipparcos's reach by several orders of magnitude. So you can kind of see here, if you can discern the dot in the center of that image around the sun. So the previous Hipparcos mission could only measure stellar distances with an accuracy of about 10% out to about 100 parsecs or so, which is relatively local in the solar neighborhood. So draw that bigger circle right out to the galactic center. That's ultimately Gaia is going to measure all those stars with that same precision, right? So it's going to make an exquisitely precise map of the positions and velocities of stars in our galaxy, right? It ultimately is going to have sensitivity to basically all stars throughout the Milky Way galaxy, right? So here's the other side of the galaxy right here. Okay, so it's going to measure motions of billions of stars or so to an accuracy of about 1 kilometer per second out to this distance. Okay, so you can probably imagine this is going to be great in terms of making a huge impact on the structure of our galaxy and the structure of stars. Many aspects of astronomy that these measurements hit on. I've listed a few right here. Like I said, the focus of my talk will be try to understanding what we understand about what we can learn about the properties of the Milky Way, and ultimately kind of try to connect this maybe even to the nature of dark matter. I should actually also mention that Gaia not only is able to measure the transverse velocities for lots of stars, for some fraction of the brightest stars, it will also measure the line of sight component of velocity. So it'll basically give you a 3-dimensional solution for many stars in the galaxy. And it's already up to, at the moment, about 7 million radial velocities that it has. So 3-dimensional solutions for 7 million stars already. And we're only halfway through the mission. Okay, so let's whet your appetite a little bit here. What does the Milky Way look like to Gaia? Okay, so here is a slice of stars sort of right in our local solar neighborhood. Okay, what we're plotting here is the z. If you look at the left-hand panel, you're plotting the z component of the velocity, right, in the position above the midplane of the galaxy. So there's kind of just a cartoon of the galaxy up there on top. And okay, what you see here is kind of straightforward. Most stars are kind of clumped, right, in terms of the z component of their velocity at relatively low values, tens of kilometers per second. Most stars are located, 100 or so parsecs above and below the galactic plane, right? If you squint a little bit on the left, you can kind of discern a little bit of a spiral structure developing. But if you do something different and plot those same coordinates, but you bin it not in terms of, say, density, but you bin it in terms of, say, the azimuthal velocity of the star in the plane, you get this really interesting spiral-like structure, right? So this tells you that something's going on in the Milky Way galaxy. The Milky Way galaxy, if you will, is not completely phase mixed at the moment. That's a bit of a technical term. But this is actually giving us clues of some recent event that happened in the Milky Way disk, right, that formed this structure in the phase space. Okay, so what are those possible things? Well, one possible thing is there was an impact of a smaller galaxy, right, near the midplane of the Milky Way, right, that sort of stirred up the stars in this particular fashion. Another possibility is, there might be sort of resonant interactions of stars with spiral arms in the Milky Way, which causes this distinct pattern. To me, the first, we don't know yet what happened. We don't have a perfect explanation for this. To me, sort of that first idea is really interesting because it is exactly kind of what we predict in theories of hierarchical structure formation in dark matter. We had a question in the audience, yeah.
Yeah, so I noticed you said like something happened to like kind of must have happened to like the Milky Way recently.
Yeah.
Like recently, do you mean like
Oh.
the past few years or like?
Oh yeah, well, I mean like recent in astronomers' definitions, right? So like 100 million years ago. So it wasn't yesterday, unfortunately, right? So yeah, so recalibrate your definition of recent, right? For the sake of this talk. Good question. Thank you very much. Actually, a very good question. Go with that. Okay. So, right, let's kind of push back a little bit on this idea, or push forward a little bit on this idea that maybe there was an impact, because I said this is sort of along the lines of what we predict in our theories of the formation of the Milky Way. Okay, so what you're looking at here is a numerical simulation of a galaxy which we believe looks like and formed like our Milky Way galaxy does. Okay. What you're seeing here is a lot of structure in this image. So the disk of our Milky Way galaxy, which I was showing, kind of would live that little bright dot in the center. Okay. But what you're seeing here isn't visible light. What you're seeing here is actually all dark matter. Okay. So, and sort of these dense concentrations of light, right? They're not like luminous stars. It's just, over densities of dark matter relative to the smooth components of the galaxy. So you can kind of see here that our Milky Way disk, our Milky Way galaxy, and our Milky Way disk on a grand scheme of things is just a small component of our entire galaxy. So what you're supposed to take away from this, these types of simulations, which have now been going on for several decades, and are now getting very high resolution and making very exquisite predictions. There's really two key properties of dark matter halos, so-called, like the Milky Way. One is that they have so-called universal density profiles, right? The density in the center falls off in a particular way relative to the density in the outer regions. So that particular model goes by the name of a Navarro, Frank, and White model, after the authors who first started doing these simulations and analyzed this back in the 1990s. And in addition, you'll notice that there's not, the halo is not all completely smooth. There's lots of so-called substructure or subhalos in the Milky Way galaxy, right? So our galaxy is teeming with these types of objects, which are much less massive than the Milky Way, but nonetheless are still predicted to be there. And in particular, most of these objects are predicted to be completely dark and have no stars associated with them at all. Okay, so those are kind of two fundamental predictions of this cold dark matter model and this hierarchical structure formation theory of the Milky Way, which simulations have given us over the past several decades here. Okay, so kind of just keep this in the back of your mind, because really this is going to be really just the key. We're referring to this theory a lot through the rest of this talk here. Okay, so there's an additional aspect to this hierarchical formation structure theory, which is really interesting in the sense that we have these like smaller bodies being accreted into the Milky Way galaxy that we saw and that we still see here in this image. But as these bodies fall into the Milky Way, right, they will get tidally destroyed, right, by the larger gravitational potential induced by the Milky Way galaxy. Okay, so if you look into these simulations, you see debris and streams that are associated with the tidal disruption of dwarf galaxies all over the place. Okay, so here's a particular map. So I kind of, not to scale here, put our Milky Way disk inside this dark matter halo in a cartoon type fashion. And then you see the sun, right? So what do these simulations predict for, say, the distribution of the dark matter in the solar neighborhood? Well, it turns out there should be like lots of debris, right, from these dwarf galaxies, right, that got disrupted. And now we see, right, if we could in principle see the dark matter, we'd see sort of this rich structure and velocity space, right, which is what you see here in these images, where if you can discern the colors here, these are just two different projections of the velocity of particles here in the solar neighborhood. Each sort of group of colors came from a different, object which came in and got tidally disrupted. Okay, so we might predict anywhere from several hundreds of these streams, if you will, in our solar neighborhood. So right, we have our predictions now are universal density profiles of dark matter halos, lots of substructure, and lots of debris, right, which originated from these galaxies to begin with. Okay, so those are going to be kind of themes going forward here. And what we want to do here is test this model, right, with observations amongst them, these astrometric observations that I'm talking about. Okay, so let's talk about, I think I mentioned the word dwarf galaxy. Let me actually define precisely what that is in this context here, right? You saw those little knots of, I call them substructure or subhalos, and I said most of those will be completely dark, right, or predicted to be completely dark in the theory. However, some small fraction of them are observed to host visible galaxies and have stars associated with them, okay? That's interesting because we see, you know, several dozen small galaxies orbiting our Milky Way, right? Which we believe to be, according to this theory, residing, right, in those substructures or subhalos, okay? So we haven't completely mapped out the entire sky, right, to find these faint dwarf galaxies at the limits that we need to. As you can see here in this image, which is unfortunately behind the zoom bar. Casey, are you monitoring the chat? I think we have 2 chats here, I just realized. They weren't questions, okay. I'm gonna test my skills on moving the zoom bar. Okay, failed. Okay, all right, so, right, so you can kind of see it as gray areas, sort of the north and south galactic caps, which have been mapped out pretty exquisitely by different surveys over the past several decades. And we've discovered, like I said, probably upwards of 50 of these dwarf galaxies now. And according to our theory, we believe these live in these dark matter subhalos. Okay, so it's an interesting way to classify these dwarf galaxies behind my head here is in terms of this figure here, which shows their size versus their brightness. And sort of on the right-hand side of this plot here, you see the dwarf galaxies. Okay, these are sort of the blue squares. These are similar, but not exactly like the globular clusters of the Milky Way galaxy, which sort of reside on the left-hand portion of this plot. Okay, and sort of the natural dividing line between a dwarf galaxy and a globular cluster, right, is essentially this figure, right? This has long been used to define the difference. Physically, the difference is essentially all of these dwarf galaxies are dominated by their dark matter mass. Okay, very few stars associated them with relative to dark matter. Globular clusters, on the other hand, typically don't have dark matter associated with them. Okay. So these, what I'm pointing at here, are sort of the faintest galaxies in the universe, if you will, and we can only see them very locally. Okay. So what I'm particularly interested in doing is using these galaxies here. I said they're mostly dark matter, using them to test sort of this universal dark matter density profile hypothesis, this Navarro-Franken-White model, because that gives us a hint, okay, these simulations are simulating the right dark matter model. Okay, so the way that we can actually do that is to take observations of stars in these galaxies. Okay, so this is a particular dwarf galaxy called Sculptor. You know, you're here making the observation on the Earth. And what you typically see here is the motion of a star, like I said, going along your line of sight, right, and back. Also, you can actually, in potential with astrometry, get the tangential motion of the stars in the plane of the sky. Okay, so most of these galaxies only have their line of sight velocity dispersions measured. Okay, so that means we can only use those to probe the gravitational potential of these systems and therefore the dark matter components. Okay, so one topic which I've been interested in for a long time here, as you can see, is if we can actually get the astrometric components of the stars in these galaxies, this would actually greatly improve the solution and greatly improve our potential to determine how much dark matter they have in them and potentially go forward with this to test this universal profile model. We are now entering the age where that's possible. So I hope to convince you that here going forward. Okay. Okay, so just to be a little bit more precise here about this. So on your left here, right, you see the line of sight velocity dispersions for stars in these galaxies, right? You just take their velocities, right, you know, bin them up, calculate the second moment of that distribution. It's pretty straightforward. And then that's basically, in some sense, a function of the dark matter mass in the system, right? So, so for a long time, the measurements on the left have been done, okay? And we have exquisite maps of these velocity dispersions. Unfortunately, although we can tell from these measurements that they have a lot of dark matter in them, we can't actually tell, you know, what kind of dark matter profile do they have in them. So we can't precisely test the Navarro-Franken-White model. right, 2-ish years ago, were the first measurements from Gaia that came out. We're actually now able to start to resolve the tangential components of the velocity of these galaxies, and that's what you see here on the right. It doesn't take a seasoned scientist to look at these and say the measurements on the left are much better than the measurements on the right. But the measurements on the right are better than nothing we had several years ago. Okay, so we're now starting just to get into this epoch where this is possible. We're not yet able to discern, well, like I said, what kind of dark matter profile that the systems have. Okay, we hope to do that going forward. So we did make a prediction a few years ago, more precisely, that you need to get down to an equivalent transverse velocity of something like 1 kilometer per second or so to start to really determine, what this dark matter property, what this dark matter distribution is in these systems. And the thought is, and the hope is that, maybe with future Gaia data releases, we can get there. Okay, because we're only about halfway through the Gaia mission. Okay, what actually can we do, right? At the moment, we can't measure internal density profiles for dwarfs. Hopefully we can. But we can do, Gaia has all sky data. We can actually just look and see what's going on in that region of one of these galaxies, right? So this is a particular image of the Sextans dwarf galaxy. And you can kind of see here, that's a very crude cartoon there in your upper left. If you look at a simulation of a galaxy like this, I said, you kind of see the central region, but you also kind of debris floating around from the galaxy. So, so the thought here is it's possible if you just look and sort of map the data, the kinematic data with Gaia around a galaxy like Sextans, you can actually potentially start to discern, is there tidal debris associated with this galaxy, right? That's predicted in theory. And whoa, hello. Okay. So we are actually doing that right now in a paper which will appear soon, led by Claire and Paul. We're actually mapping out the region around several of these dwarf galaxies, and we're actually finding some interesting hints that there is, several stars that are consistent with being members of this galaxy, right? But that sort of exists sort of in the outer regions of the galaxy. So it might be hinting at first evidence that we do see some tidal debris associated with these systems, which would be really interesting. Another thing we can do with the current Gaia data, even though we can't measure the dark matter properties of dwarf galaxies, we can actually look at globular clusters. And globular clusters, I said, are really interesting. By and large, they don't contain dark matter, but one particular globular cluster is really interesting because it contains something else besides stars in it. This is a globular cluster Omega Centauri, which exists in that very peculiar region of this parameter space here. So Omega Centauri is only about 5 kiloparsecs away from the sun, which is very close on astronomical scales. And it actually has exquisite 3D kinematics mapped out by several surveys, including Gaia. So what we're doing here is looking at all data sets, including Gaia data, to try to really map out, how much dark mass does Omega Centauri have in it. And we're actually finding that, very interestingly, this Gaia data combined with other data sets does sort of really hint that there's something else going on in there besides the luminous component. So there's a dark matter mass associated with Omega Centauri. And this paper is led by Addy, which will appear pretty soon. Okay, so talking about the velocity component of the story here, let me add a little bit of a twist to the game here, right? So when we look at a dwarf galaxy, we see their stars in projection, right? We see just a 2-dimension where they live, right? We can't like look at an individual star and say, I know exactly where that star exists inside that galaxy, right? We just don't have the resolution to do that. It's hard to point at an individual star and say, I know the distance to that star. That's sufficiently far away. But there are particular kinds of stars you can do that. You can measure, say, a period luminosity relationship with stars. You can calibrate this to get distances of stars. And this is classically done with Cepheid variables. We've heard a lot about this over the past few years here. The particular star we use to do this for dwarf galaxies is a star called an R Lyrae. And I won't really go into detail about why that's true, but just, for the context of this talk, just think that this is a star that we can have a pretty good sense of its distance, to and away from us based upon its the properties that we measure from it. And you can see here in a map that's made, you can kind of sort of by eye, this is an R Lyrae map. This is made by Caitlin Stringer here, graduated a couple years ago. You can actually look and pick out the dwarf galaxies in this figure, right? So that's the sculptor dwarf. It's a little bit elongated, right, along the direction of the observer, just because, the uncertainties in those distances. This is the Fornax dwarf galaxy. It's a little farther away, so it's a little bit more elongated. But the idea is, right, what if we add sort of this 3-dimensional description of the distance to these velocity components. How does this help us understand these properties of dwarfs? So, right, this is a topic I've been really getting interested in recently. So we're going to sort of look into more detail at these types of observations. We're going to use this galaxy called the Sagittarius dwarf galaxy. You might ask, why are we using Sagittarius? So here's a cartoon image of Sagittarius. It is very bright relative to other dwarf galaxies. It is relatively nearby, right? About 25 or so kiloparsecs on the other side of the galaxy relative to us. It's very interesting, and it has tidal debris, very visible tidal debris, just emanating from all around the galaxy as this thing is evolving in the Milky Way. So you can kind of see evidence that it's getting tidally destroyed. Okay, so it does have sort of a centrally bound core associated with it. Okay, and Sagittarius is close enough, so its stars are bright enough that you can actually look at its aurora lyrae in the core to try to map out the three-dimensional structure of the system. And that's something we did with Peter Ferguson, who recently graduated. So we looked at these aurora lyrae, and we actually determined that the shape of the stellar distribution, right, it's not a perfect sphere, right? It's actually triaxial. So there's interesting stories about how that triaxiality is oriented relative to the galaxy that I won't get into, but this is actually sort of the first dwarf galaxy that we're able to do this type of measurement with, because at the moment it's the one we can do because it's relatively close. As we'll mention in a few minutes here, we're kind of looking to take this a step further with other galaxies. Okay, so we could do that with these particular stars, these aurora lyrae and Sagittarius. You can also use Gaia actually to take the brightest stars, not necessarily aurora lyrae, but just the brightest stars in Sagittarius. And actually, you can measure the three-dimensional velocity dispersion like right now, right? It's just that bright. Sagittarius is dark matter dominated. The central core is. Each of these three components represent the three components of the velocity that have been measured using this sample of bright stars called red giant stars in Sagittarius. Okay, there's dark matter solutions which are painted in blue. I'm unfortunate to report at the moment, once again, we can't determine sort of this density distribution of the dark matter in the system, right? But this is actually, at the moment, the only dwarf galaxy that we can actually make this measurement in, right? And like I said, these measurements will continue to improve going forward here. A really interesting project that we have going on at the moment, led by our postdoc Therese Hansen and Peter Ferguson as well, is we have time on the VLT, which is the telescope in Chile, to measure the velocities of the aurora lyrae in Sagittarius, right? So why is this interesting? Because if you get the radial velocities for these stars, right, this actually is sort of the first sample of stars, and we'll basically have the whole six-dimensional phase space covered, right, for a sample of stars in the galaxy, right? The three components of the position, three components of the velocity. And I won't get into how much cool detailed dynamics you can do with this, but believe me, you can, right? And those are some observations we're looking forward to getting in the near future. In fact, I think we got our last set of observations a few days ago. Okay, so that's the story with sort of the internal structure of dwarf galaxies and why they're interesting in the context of dark matter and kind of where we're going with this game. Sort of, if you look at sort of the position and the spatial structure of these galaxies around the Milky Way, you actually find something peculiar. So now here's a cartoon done for Andromeda, which is the nearby galaxy relative to the Milky Way, but the same story happens for the Milky Way. If you look at how these galaxies are distributed around our disk of our Milky Way galaxy, you find they kind of preferentially exist in a plane of satellites. And I'm sorry for the zoom bars in the way here again. Okay. So this observation's been made not only for Andromeda, but also for the Milky Way. And this is called the polar plane of satellites. Okay. So the question is, why are preferentially all these satellites kind of lying in a particular plane, right? Is that some peculiarity of how the system formed? Possibly, right? Does that mean that our simulations need some work in terms of determining how these formed, right? That's a question that's up for debate in the literature. But this is an observation we have at the moment. Okay, so we kind of wanted to push back at this a little bit. So this is a paper that Alex wrote a couple of years ago, asking not only this question, do the dwarf galaxies preferentially lie in the plane, but using the data from Gaia, amongst other data sets, do globular clusters, do stellar streams all lie in this plane as well? And he did some detailed orbital models for all these systems, and I'll kind of spare you the details. This figure here is a little bit of a detail on the right, but the answer is no, right, at the moment. So this could tell us, that something about the formation histories of globular clusters and dwarf galaxies. They're sort of sampled from different populations. Their orbits evolve differently in our Milky Way. One sort of side product of this analysis is that Alex and Therese were able to look at a particular globular cluster, NGC 3201, and they were able to identify that you have the cluster here, and there's a stream of stars out here, right? Right. You look over here, there's a cluster. You look over here, there's a stream. But those things are actually kinematically connected with one another, right? And connected based upon sort of their abundance structure. Okay, so we actually followed up and did some detailed observations, and made a link actually between, say, a stream and the core of the cluster. And this is actually, there's only a handful of objects in which this has been done before. Okay, so but data from Gaia is now allowing us to do this and sort of understand how these clusters are evolving within our Milky Way. Okay, so let me back up one more step here, talk about the local group. I mentioned the Milky Way and M31 or Andromeda. So these two galaxies comprise our local group, okay, along with the associated dwarf galaxies around the Milky Way, around M31. And there's a few dwarf galaxies kind of sitting in Never Land between and around all of them. So, right, you see the coordinates on the left. You see the picture of a cosmological simulation of a system that looks like our local group there on the right, where you see those two bright objects, the Milky Way and M31, are kind of barreling towards each other, right? So that's actually precisely what's seen in observations. So the question is, can you sort of use the kinematic structure of the observed Milky Way and M31, right? They're measured distances, they're measured velocities, to understand how much dark mass, if you will, is in the local group. So this actually analysis goes back to the 1950s, where you just assume the Milky Way and the M31 are on a Keplerian orbit, solve the equations of motion, and then you get much more dark mass than luminous mass in the local group, something like 5 times 10 to the 12 or so solar masses. Okay, this analysis actually goes by the timing argument. Well, actually nowadays you can actually look in these large-scale cosmological simulations to identify these systems and say, and sort of, if you will, like calibrate this type of observation. Okay, with this new, in particular, you can actually do this very precisely with new tangential velocities from Gaia. So that's something we did with Adelia, who just started here as a graduate student. So she started this as her RU project a couple years ago. So she looked at this and calculated the dark mass associated with the Milky Way, and like I said, got something like 5 times 10 to the 12. Compare this to kind of a more standard cosmological mass estimator to calculate the mass of a system using a virial theorem type analysis. And it's kind of been known for a long time that these two measurements don't necessarily agree with one another. But if you really look at the systematics of how to do this in a cosmological simulation, you find kind of the error bars are a little wider than have been appreciated in the past. So we kind of came to the conclusion that these methods are in agreement, but kind of barely, right? But either way, they're pointing towards a large amount of dark mass in our local group. Okay, so that is the story with sort of kind of doing kinematics of galaxies. So I've got maybe about 10, 15 minutes or so. I want to kind of sort of spend these last 10 or 15 minutes talking about what this implies for, or can apply for measurements of particle dark matter. Okay, so I didn't actually go into details on this in this particular talk, but you may have heard me give talks before, motivating how this dark mass around the Milky Way and around other galaxies in the universe is probably some unknown elementary particle that we've not yet identified in our laboratory. Okay, so in addition to building detectors in the lab to try to identify this, astronomical measurements can actually help in doing this as well. For example, if you look at these dwarf galaxies, right, and these dwarf galaxies are dark matter dominated, the dark matter might so-called annihilate with itself and make radiation that comes out, and this radiation is something that we could possibly observe in our telescopes. So one way that's classically been done the past decade or so to look for this so-called annihilation radiation is sort of with this high energy gamma ray experiment called the Fermi LAT satellite. So here's a gamma ray image around one of these galaxies you see kind of on your upper right there. The good news is we have a lot of good data associated with all these galaxies. The bad news is we haven't really found a signal associated with dark matter yet. Okay, but the good news is the experiments are becoming so sensitive that we're actually able to really drill down and probe into really well-motivated models for particle dark matter. So you kind of see this is the strength of the annihilation cross-section versus the dark matter mass in a region of parameter space that one often considers here. You really need to know the details of how this line gets computed, but know that this is a really theoretically favored region. And these observations now tell us that the dark matter has to be sort of below this line of the observation. So a lot of this preferred range from cosmology is now becoming ruled out. So that's really one of the great contributions from Fermi over the past decade or so. Okay, like I said, these observations they're really interesting. Where do we go with these types of analysis? Can we improve these measurements with in terms of bounds on annihilation radiation? So I'll just highlight a couple of reasons, a couple avenues that I think are particularly interesting about ways to do this. One is actually go back to Sagittarius, right? People have ignored Sagittarius in this game for a long time because they're kind of afraid of it, and rightly so, because it's kind of sitting right behind the galaxy. There's a lot of junk, right, that's going on between in the foreground between us and that galaxy, and there's some of that junk you can kind of see in the upper left portion of that plot. But it's large, it's dark matter dominated, it's relatively close by. I think we got to go for it, right? So here's the most recent upper bounds of gamma rays from Sagittarius. Particularly if we get these observations, like I was saying, these sort of 6-dimensional observations of the positions and stars in the system, we could map out its dark matter distribution and sort of help us get better predictions for what this radiation flux is supposed to be. So this is analysis we're kind of working towards at the moment, and hope to have some results out about this soon. So let's go back to this peculiar object called Omega Centauri, which is kind of like a globular cluster, kind of like a dwarf galaxy. It's not clear what it is, but it's something. So there's Omega Cen. Omega Centauri does actually have a gamma ray signal associated with it. So there is radiation coming from that system. The question is it dark matter or not, in the sense that I'm describing? Well, we don't know. Okay. What is likely true is that there's these objects called pulsars, which are emitting radiation. Basically, they're remnants of supernova explosions, right? And they're emitting high energy radiation sort of in the same energy band. We've identified some pulsars in this galaxy, or in Omega Cen. So it's certain that some of that radiation comes from pulsars. The question is there room for a dark matter contribution to Omega Cen? And we speculated a couple of years ago that there could be a dark matter interpretation to this signal, right? We don't know what the answer is at the moment, but it's very clear if there's some dark mass associated with it and it's very close by, then we should actually pursue this even further. Okay. So that is on gamma rays. So let me highlight another particular analysis. So all the bounds that I've shown up to this point assumes a peculiar property of the dark matter, in the sense that it's sort of how it annihilates with one another doesn't depend upon the relative velocities between the particles. You can actually take these models, you can actually make these models arbitrarily sophisticated, quite frankly, but one sort of simple next step is to make that cross-section dependent upon the relative velocities between the particles. And this is actually kind of not only interesting from the perspective of particle dark matter models, it's also interesting from the perspective of astrophysics, because then your signal now depends upon how the dark matter is distributed in velocity space in the galaxy. Okay. So in the upper left-hand image there, you see kind of if you will, an annihilation radiation map of our Milky Way galaxy, as well as the substructure associated with it. And you can actually sort of predict what the structure of this radiation looks like by going into the simulations I was talking about earlier. So what we did in a recent paper was we considered these velocity-dependent models, where, like I said, the cross-section depends upon the velocities of the particles, so it depends upon how these things are distributed in velocity space. So we kind of made the first predictions for based on these simulations about how what the strength of these signals are for these different models, and actually found something really both interesting and boring in the same way by looking at these simulations, right? If you calculate sort of the relative velocity distribution, we're kind of maybe expecting to see some structure, right, in velocity space. So we didn't, right? They kind of looked like a perfect Maxwell distribution, right? So in some sense, that's good, right? Because our theoretical predictions are now pretty well grounded, right? If you were kind of rooting for some sort of interesting astrophysical phenomenology, unfortunately, doesn't appear to be there. And this was a paper led by Aaron a few months ago. All right, so let me kind of end up here in the last few minutes talking about sort of local, very local dark matter and sort of implications for these types of signals. So, there's about 1 dark matter particle in your coffee cup or so, more or less, according to our theories. There's experiments that are now being built to try to detect that dark matter going through your coffee cup. The signal that these experiments see, right, depends on 2 things, right? It depends upon sort of what the interaction strength of the dark matter is with the material in the detector. But it also depends upon, how fast the dark matter is moving, right locally. And that's sort of the how fast component is the component you can get from these simulations. And so here's a high resolution simulation of the solar neighborhood in dark matter. You plot the velocity distribution here on the lower left. And once again, you can kind of see there's like some structure in this distribution. That's just the velocity on the x-axis there. You kind of see some structure, right? But this kind of looks more or less like kind of a standard Maxwell distribution. So, ideally what we'd like to do is, detect the dark matter, get its interaction strength, and then, ultimately maybe map out this local structure. I think we're a little bit far from there yet. These experiments are actually becoming a victim of their own success, quite frankly. So here's the mass of the dark matter particle. Here's the interaction cross-section with dark matter with, say, the material in your detector. And various experiments going on around the world are mapping out different regions of this parameter space. Okay, so and these experiments are becoming so sensitive that they're getting to a point where you have a background that's going to come in from neutrinos from the sun and neutrinos from the atmosphere, right? Because those neutrinos are going to basically make the exact same signal in your detector that a dark matter particle would, right? So in some sense, this is good, right? Because we can detect these neutrinos. In some sense, it's bad if you're looking for dark matter because, maybe it's going to become a lot harder. Okay, so let's kind of be an optimist, right, and figure out like what we can do with the neutrinos here. Nice and bar. So there's many papers that have been written the past decade or so trying to determine how, say, you differentiate between a dark matter and a neutrino signal in these detectors. There's a WIMP wind due to the motion of the Earth around the sun. So you get a time modulation in the dark matter signal. You similarly get a time modulation in the solar neutrino signal due to the slight eccentricity of the orbit of the Earth. There might be sort of crazy effects going on in the solar neutrino signal that we don't understand. And we kind of spent some time exploring these types of signals. Right, if you had a detector that could actually not only tell you, that an interaction happened, but also the direction from which that neutrino or dark matter particle came, then you're golden, right? Got everything. You could even, go back and try to map out this phase space distribution of the dark matter locally. The problem is we're really, these directional detectors are not there yet in terms of sensitivity, but it's something we can actually think about. We do have sort of projects to try to look at these directionally sensitive detectors in the context of neutrinos on the Earth that we're thinking about right now. It's a little bit of a side point, but if anybody's interested in that, feel free to talk to me about that. Okay, so we're still thinking about this. We're trying to understand the signal. Sort of for my last topic here, I want to say that we're looking now, one thing we're looking at here is there's not only a time variation in the solar neutrino signal, but there's a time variation in the atmospheric neutrino signal in these detectors as well, because at these very low energies, the cosmic ray flux, right, depends upon the 11-year solar cycle, right? So cosmic rays come in, hit the atmosphere, make neutrinos, right? The neutrinos we then detect, right? But at these very low energies, right, cosmic rays interact with the solar wind, right? And there's an 11-year solar cycle, so that thing changes. So we actually are trying to do the first calculation here of how this atmospheric neutrino signal changes in time in the detector. And this is a paper led by Yi, who's sitting in the audience here. So she's performing the first calculation of how this atmospheric neutrino signal modulates at these low energies. And there's actually lots of interesting phenomenology here associated with this signal that I don't really have time to get into. You could see contributions, from new physics interactions, right? If you can really understand how this works. And so this is really important, right? Not only to try to, understand sort of where that neutrino floor is in the dark matter signal, but also to try to understand, this signal, right, that we would detect of low energy atmospheric neutrinos. So I'm about done, actually. So what I hope I've convinced you of is that, so we're kind of entering a new era of, like I said, measuring positions and velocities of stars, right? Something astronomers have done for a long, long time. And now we're just doing it really, really well. I hope I've convinced you we can actually use those measurements to try to probe, if you will, fundamental physics and try to push at, how using these observations to learn about the nature of dark matter, not only locally, but also how it's distributed sort of around our Milky Way galaxy. So that's that. If there's any questions, I'll just hand it over to Casey.
Please help me. Thank you.
Okay, I think I've got this back on too. That was great.
Surprised my battery collected them.
Yeah, good. We have battery light.
Oh, I got one bar left.
We'll take questions here in the audience. I'm also going to watch for anything for the people. There are 50 people online, so please raise your hand, use that icon. I'll do my best to call on you. And then I'm going to remind us all to repeat the questions that were here in the room for the sake of the people on the Zoom. I saw Peter's hand first, so we'll start there.
In this array of dark matter clusters near the Milky Way, is it possible yet in this wealth of information we're pulling together to, in some sense, try to turn the clock back and understand the dynamics of formation? Are they consistent with a model in which the dark matter clusters formed organically in situ as the galaxy formed and evolved?
Yeah.
Or did they come streaming through in the fashion that the galaxies and nearby star masses pass through and interact?
Yeah, so actually you want to go.
Do your best to summarize.
Okay, so Peter is asking basically, with these observations, can we use them sort of to deduce the history of what happened to the dark matter, right, and the stars? Did they sort of form in situ in the Milky Way, or was there more of like a hierarchical process where things merged together? And so the prediction of lambda cold dark matter theory, which I've shown here, is that it's, try to the former or the latter, it's the hierarchical one, right? So this is a theory of hierarchical structure formation where smaller things form first, accrete to become larger and larger things like our Milky Way galaxy. That's the prediction. So the question is that consistent with what we observe with this data? And I'll say at the moment, it's not inconsistent with it, right? You see this debris, right, from these galaxies that are being accreted in. You see, I didn't really get into the subject of stellar streams in the Milky Way, but that's just like that's like a whole different talk, right? So that debris is believed to be associated with this hierarchical accretion process. So if I was an optimist and I was solely responsible for writing down the lambda cold dark matter theory, I would say 100% absolutely it agrees with my prediction. So I think at the moment it's yes, right? There's no reason to bail on this because of those observations.
Actually, I go one step further and just say it seems like over time it's gotten closer. The observations are getting closer to the predictions. Which is really interesting.
Yeah.
Appreciate.
So, well, you mentioned that globular clusters essentially don't have any dark matter component. But what is the confidence behind that statement?
Yeah.
Because I find it strange that the other globular cluster,
Yeah, Omega Centauri, yeah.
right? It has some component.
Yeah, I mean, so Omega Centauri is kind of peculiar. Okay, sorry. Yeah. So Greece is basically asking, I made the statement that most globular clusters don't have dark matter. Greece is asking, do you really know that? Okay, so observationally speaking, right, you can look at the globular clusters, look at the kinematics of the stars, most of them, and say, okay, they're consistent with not having any dark matter. I can just look at the stars associated with them and say, the mass I can attribute to that. Omega Centauri is a little bit different, right? Actually, there's two aspects of this story. Let me address the first part first. Even though I said globular clusters are not consistent with having dark matter, that does not mean they don't have dark matter, right? There might actually, there's theories that have predicted that globular clusters sort of were seeded by dark matter halos, if you will, and they got, the stars and the cluster got accreted into the halos. But the dark matter halo for the clusters got stripped off by some process, which models have been tried to deduce how that happened. That is actually a possibility, right? That's a possibility. So it is possible that basically all globular clusters contain some amount of dark matter. They just don't dominate the mass component. Omega Cent is just like different. It's just like it looks its size. It looks like a globular cluster, right? About 10 parsec half-light radius. But it's sort of, when you look kind of in details of the population of stars, it looks kind of a lot more like a galaxy. So really, for many years, there's been this thought that Omega Cent is actually kind of the, tidal remnant core of a stripped away galaxy, right? It's kind of traditionally just been classified as a globular cluster just because it kind of in size space looked like one, and it didn't have a lot of like dark matter associated with it, so it's probably fine. So yeah, so these are actually really active questions of research. People are asking, like, how much dark matter could be associated with these things. It's a really legitimate question.
Other questions from the one at the back and then one at the front.
He was in my class last year.
So you mentioned the dwarf galaxy on the opposite side of the Milky Way.
Yeah.
Being studied. How much does the Milky Way get in the way of observation?
Excellent question. A lot. A lot. This was discovered in 1994. Oh, sorry. Yeah, thank you. Okay, so the very good question from the audience was this object Sagittarius, which is behind the Milky Way galactic center relative to our location in the sun. How much does sort of the intervening Milky Way screw up our observations of that? And the answer is a lot. So it's very bright. It's amongst the brightest.
Very scientific, but
A lot, yeah. You got that? So it's amongst the brightest dwarf galaxies that exists, but it was, many of these dwarfs were discovered a century ago, just because they're bright enough. This thing was discovered in 1994, right? But it just couldn't be found because it was like, you got to go through a lot of crap on your way there. So yeah, they're actually like, and actually, if you look at this, that's scientific too, right? Yeah, okay. So yeah, there's reasons there's holes in this figure, right? Right where the galactic plane is, right? So there's probably lots more dwarf galaxies that exist. And, this has been a debate that's been going on for, at least a couple decades, at least as long as I'm thinking about this, right? How many more are out there that we're just missing because we just can't see them? Yeah.
I'm not really familiar with this. So could you explain in more simple terms what the relationship between dark matter and neutrinos are?
Oh, yeah. Okay, so what's the relationship between dark matter and neutrinos? Okay, how much time do you have? So we'll try to keep it simple, right? Neutrinos are a light, mysterious elementary particle of nature, right? That we know pretty well the properties of. There's still parts of it we don't really understand, but we kind of know decently how well they interact. And maybe you're well too young to have lived in the 1980s. I'm barely that young. But there was some sense back in that time that neutrinos were the dark matter, right? Because they're weakly interacting, they're perfectly fine. They kind of just, a bunch of them are kind of going through our room right now. It turns out that actually, for some technical reasons, that actually can't be true. So there's another sort of elementary particle of nature that we call dark matter, because we don't know what it is at the moment, right? But so our evidence leads us to the direction that it is some new particle, and they can kind of like interact in similar ways, right? So if you look at a detector and say, okay, there's I see something happen in my detector, there's a sense that we don't know whether that's like a dark matter or a neutrino, right? You have to kind of like deduce that based upon the properties of the neutrinos coming in, and that's a little bit where I said towards the end, right? This slide here. Yeah, that's the game that direct dark matter detection experiments are playing now. Rupak, I see his face here on that's right, is building detectors, and the idea is to try to detect a dark matter signal, but it also might actually be try to like use these to see what's going on in the neutrino world as well. Yeah.
I mean, some of them, they're obviously the light neutrinos, not the dark matter world.
They are, but they're moving too fast.
The neutrinos.
The neutrinos are moving too fast. Is that scientifically technical enough for you?
They're too light.
They're too, well, yeah, okay, combination of both.
Yeah.
Okay.
Fair enough.
Yeah.
Any more questions from the audience? And I've been neglecting my duties here on the chat. So I see one hand raised there. I'll call on Nick Sunset. Nick, if you take yourself off mute, I'm not sure what happens.
Okay, thank you. Great talk, Louis. This
Thanks.
may be far afield, but Sagittarius is a really weird galaxy. It's like it didn't have any massive stars. in its chemical abundance. It's missing all sorts of heavy elements. Do you have any ideas why there would be a light, not a top heavy, but a light heavy IMF to a galaxy like that? Why would it be so different than everything else that we've seen?
Yeah, so the question is like Sagittarius appears to be very peculiar, right, in terms of its abundant structure of the stars in it. And Nick is asking me why that is, and I'm just going to say, unfortunately, I don't know. So at the moment, we actually don't know. So Sagittarius, we see it right now, but there's a question I think from Peter, like, what was it like, giga years ago? Was it a disk galaxy? Was it more elliptical-like galaxy? We don't even know those basic answers to that question, right? Much less, its chemical history. Those are at the moment kind of like beyond the realms of simulations. But I mean, I agree the observations are actually peculiar. That's just something that we'll have to, sort of in this realm of like dwarf galaxy formation at these dwarf galaxy scales. There's lots of processes which actually are not really well understood, right? And that's, you can sort of count that question amongst these processes, which are not well understood at the moment. So yeah, I mean, that's a good question. Unfortunately, I don't have a better answer for you.
Can I ask one more question? What do you think is the solution to the cusp core problem?
What do I think the solution to the cusp core problem is? And my answer to that is there a cusp core problem?
Okay.
I'm actually not of the belief that okay, so cusp core problem. So Nick's question is there, what do I think is the solution to the cusp core problem? And so let me just show the diagram here. So there's been volumes of literature saying that the density distributions of the dark matter in these dwarf galaxies don't look like that NFW model that's predicted, but they look more like those flat models that are shown there. And those flat models are called chord models. And if that's true, that would mean the dark matter is behaving differently than we believe it is in our simulations. And there's been lots of noise saying that those observations are more consistent with the chord model. I contend that observations at the moment aren't good enough to discriminate between those models. So I guess the answer to your question is I don't know that at the moment we're good enough to say that it's a problem.
Thank you.
Mm-hmm.
Okay, I think that I will thank Louis for a great talk. Now we're fine. So if you have additional questions, please come out and